All right. So we know how to quantify the injury stored in a spring. We know how to quantify the injury stored in the motion of an object. And so that's kind of where we're going to go from here is figure out the injury stored in gravitational interaction. It's an interaction and an injury because it requires multiple objects, okay? Like you don't have this if you just have the Earth. You have to have something interacting with the Earth. So the basic gist of this is, if you think about the lull, either I'm going to have my Earth in the system, and then my object, it can be some kind of a ball or something, okay? Either I want this to go from, let's say, 1, 2, 3, 4, all EG at A to all EK at, well, that's terrible, all EK at B. Or I want it to be all EK at A and all EG at B. Okay. So we put, like you're saying, so we know where it's at the top of its motion. Is that what you're telling me?
Maybe. I was imagining that putting on the board and having the thing through so that the ball just way up and the ball just on there so they don't have it.
Yeah.
So when you get out
All right. Well, I'm thinking like something along these lines. Right. Like I got this thing here. This is 4 kilograms. Right. I lift it up here. Josh, go ahead and put your fingers down there. Is there? It's pretty small. Just your smartwatch. All right. So, is there much potential for injury here for Josh if he puts his fingers down? Yeah, like how is it stored? How is it stored up here? Gravitational interaction. Gravitational interaction, right? That's where the potential for injury is here. It's not moving right now. It doesn't have any EK. It has EG, 4 bars or whatever. Okay. And if you think about it, if he puts his fingers down here, okay, think about how that injury is stored right before it reaches the fingers. Okay. I wish I had like some grapes. Like that would be satisfying. Put some grapes in there. I don't want it orange. I want grapes. Uvas? Anybody? Grapes? No? All right. Fair enough. Grapes tomorrow. Cool. That'll work well. So you can imagine, like right before, like if I put my fingers under here right now, it's not hurting them. Okay. Because basically it's like it's not falling. It's got no EG. It's got no EK. But if I do it like this, now there's a potential for some injury. All right. What I need you to do really quick with your friends and neighbors, though, is talk about gravitational force. Okay, how does the gravitational force at this location compare to the gravitational force at this location? Run that by your neighbor really quick.
So EG is super high. All EK, it's going quite fast.
I was just talking about it.
Oh my God.
If you want any sympathy towards your grade at the end of the try, use your Chromebook for academic purposes or close the lid. All right. So I'm going to set it up like this. So let's go EG initially, EK in the end. Okay, so it's going to be EK in the end. If I drop something from 1 meter, think about what the velocity versus time graph looks like. What else do I know about the velocity versus time graph if I drop something from 1 meter? Slope is negative 9.8. So if I know that, what else can I know about this thing? I can know the time. What's the time? T. What's the velocity? 9.8 t. Okay? Because that's how slope works. All right? So 1 meter equals 1/2 of t times negative 9.8 t, aka 1/2 negative 9.8 t squared. So we can solve for the t, and you get somewhere around half a second. What is it? 0.38? What is 0.2? What's the square root of 1 point? Or sorry, what's the square root of 0.2? 0.44. Okay. So there we go. So it's 0.44 seconds. So that means that this velocity is going to be somewhere in the ballpark of 4.4 meters per second, but negative. Okay? Algebraically, you cool with what I'm saying here? Okay? Because basically the velocity is 10 times whatever the time is. All right? So long story short, I have a way of relating the height I drop it from to how fast it's going. So here's the thought experiment that I need you to run there really quick. Okay? I need you to pick a mass. I need you to drop it from, how many heights do we need to do here?
2 heights.
3, 4. Let's go 4 heights. Let's drop it from 4 heights. Okay? Pick a mass, drop it from 4 heights. I need you to figure out how much EK it has at position B. Okay? So we know how to do that. That's 1/2 the mass times the velocity at B squared. Okay? So you pick a mass. Make it unique, okay, to your group. All right? Drop it from, how many different heights did we say? Drop it from 4 heights. And calculate the EK it has at the bottom. Calculate EKB. All right? And then have a conversation about injury and recognize that EKB equals EGA. All right? You're dropping from 4 different heights. So what we want to look for here is what is the relationship? What relationship, if any, exists between EG and height? Okay, so you'll have a graph in Desmos or your head that is EGA versus drop height. Okay, thought experiment. Go ahead and make it happen with your calculators. Pick a mass, drop it from 4 heights, calculate EKB, plot EGA versus drop height. You drop what? That foot?
High, our mass is high.
And again, you're not actually doing any data collection. You're just figuring out because you can draw velocity versus time graphs and make that area be 1 meter or make that area be 2 meters or so on and so forth. So drop it from 4 different heights on your calculator. See where you land. Robbie, Ellen, Kyle. Not actually dropping stuff. Dropping things from rest. They start with a velocity of 0. The slope of the graph is what? You're sitting close to Nat, so you caught that. Schnell, as they say.
Germans.
Shouldn't say it that nicely. Schnell! Faster.
1 divided by
Pretty much I just shout Mach Schnell because it means fast. Weiter, Touchdown. Whoa. That took some effort. Yeah, again, simplified methods, right? You don't want to put everything in your calculator, just keep it straightforward. Find some different drop heights, find the velocity it has right before it hits. How much EK does it have right before it hits? That's how much EG it had to have when you dropped it, when its velocity was 0. Plot EG versus drop height. What's that graph go like?
The velocity starts at 0.
Oh.
So dropping. So from 4 different heights. So 1 meter. Drop it from 1 meter.
Yeah, so this is a 1
Where is the meter?
This is velocity. Oh yeah. So wait, so
That's a slope.
drop it from 1
Yeah,
meter.
Slope ratio.
Oh, yeah. Oh, yeah.
No, you couldn't do that too. You can do that. Don't do Pythagorean theorem with the slope.
Well, no,
It looks like a right triangle though.
It's 1 times 9.8.
No, this is